Okay, thanks. You've heard a bit about patterns already. So what I'm going to talk about now is how to architect parallel software with patterns. And so to set some context, what I'd like to do is to talk about how not to develop parallel software. So what we have in this foil is we have some initial code, we profile it, we do a performance profile. If it's not fast enough, then we kind of scratch our heads for a while and look at it and go, oh, I know, we can tease some threads out of this code here, yeah, okay, let's try that. Run that through the profiler, keep iterating this, and hopefully someday it's fast enough, and then we ship it. And the problem with this approach, anyone know what the problem is? Anyone know from experience what the problem with this approach is? Well, there's a very common problem if you've ever tried it, which is lots of times by the time you're finished with all that, you actually end up running slower than when you started. And this sounds like the kind of thing that a professor in isolation has kind of made up to justify their research. But the fact is, we see this over and over and over. And we have some experiments of our own. This is one of my graduate students was trying to parallelize a Steiner tree construction for routing. These are a set of benchmarks. These are the number of threads. And this is the amount of slowdown relative to the serial code. Right? Also, you may think, well, okay, this is, even if this isn't made up, this particular approach that I described is just some sort of straw man. Nobody really does that in industry. And the fact is, if you go to Intel and you say, well, we just bought 100 of your latest Nehalem chips that are in our current desktop machines, and all our code is running slower than before. The fact is they'll send you out application engineers, and these application engineers will take you through exactly the process I outlined in that slide. Like go in here, find the hotspots, tease out some more threads, and then hopefully they probably won't be allowed to leave the premises until you get at least a little bit of speed up. So another I don't know how pervasive this is, but I've certainly got friends in academia who would propose, well, the problem is your compiler. What you want to do is you take your initial code, use our super compiler, do some performance profile. If it's not fast enough, okay, just tell us where you're having problems. We'll go in, we'll tune up those optimizations in the compiler, and we'll keep going through this loop until finally it's fast enough and ship it. And the problem with this is that, after 30 years of compiler research in the field of high-performance computing, this doesn't offer much hope either. And so this is I'm picking on one of my colleagues here. This is this is, true life. This is not a mock-up of somebody's slide. But you see, on some, like 8-core machine or something, with a lot of work and compiler optimizations, oh boy, sometimes we get as much as a 25% speed up. So there's obvious problems with that approach as well, that we just can't, this dream that we've had for over 30 years that we're just going to take our legacy code, throw it to some optimizing power, it's going to come back and really speed up and get some mileage out of the cores. That's not working either. So then finally there's, the problem with both those approaches is that they're just so antiquated, so anachronistic. What you really need is this new language that I've developed, which really makes it much more easy to describe parallelism. So if you just code in this new cool language that I have, and then go through this loop, and then you don't have to recode your whole application because it works well, plays well with Fortran or C++. You can just code portions, and if there are portions, you're still not running fast enough, then you recode more portions in this new cool language that I have. So, and again, there are people who will, if you give them 45 minutes in a conference room, they will come and give you this pitch. And the problem with this is we've had 200 or so parallel languages so far, and there's no indication that anything remotely like this works. And if you don't believe the number 200, this is a slide that I stole from Tim Matson, in which he's actually dutifully gone down and inventoried these 200 parallel languages. Oh, microphone's not working at all.
Can we turn it on?
Okay, glad somebody's paying attention. I have a little red light here.
Mm-hmm.
It's probably just not up there. Nope. It's okay. that sounds better. Okay. Sorry about that. So, Juan, could you hear me before, or was it just painful? A little painful? Okay, all right, we're good now. Anyway, all right, let's move forward. Okay, so here are 200 or so parallel programming languages that have been offered. And when Tim Mattson gives this talk, you know, what he encounters is not, oh, come on, that's ridiculous. You know, Lamb was not really meant for parallelism or something. What he inevitably gets is, wait a minute, where's my parallel programming language that I, you know, so that, in fact, I would estimate that this is probably off by a factor of 2 in the number of actual languages that have been proposed for parallel programming. So if no of those 3 approaches actually works, then what is the alternative? And so I take a very pragmatic approach, and I spent 15 years in industry, about half of that at Bell Labs Research, about half of that at a small company that became a big company called Synopsys. And at one time I was chief technical officer at Synopsys, overseeing 25 software products. And as I did, you know, without any kind of zealotry or, you know, I did my dissertation in software engineering, just kind of observing what worked, what I found, the 2 best principles I found to facilitate good software design were the use of modularity and the definition of invariance. So modularity helps in a wide variety of ways. It helps the architect of a system, the person who's really kind of figuring out how it's all going to fit together, make the design sound and comprehensible. You know, as I kind of grew up through management, what I found was, what I loved about modularity is when I have different modules and have good interface descriptions, then I can just kind of deal out those modules to different people, and I don't have to drive home worried about, oh, you know, is Sam talking to Sally tonight? You know, that you know, they really need to get that code right together. I know that if they just get their interface specs correct and meet their contracts, then things will work out. And I'm also able to use kind of a modular tracking of the project to see how each individual module is going along. On the other hand, back in the old days, or looking at people who were in their cubicles actually implementing those modules, it's nice they get a drive home, not worrying about whether Sally changed the guts of her code, because it doesn't affect, because I know we've met our interface spec, and there's no way, no matter what she's doing on our code tonight, that she can hurt me. And then finally, I don't have time to talk more about this identification of invariance, but that's a critical feature as well. So when I told this to my students who are great programmers but have mainly done kind of, you know, programming in an academic context, they go, well, that sounds kind of like motherhood and apple pie. I mean, you know, what exactly can go wrong? So let me tell you what can go wrong is you launch, say, 6 people at a project, you know, coding for about a year and a half, and what you get is truly spaghetti code. That is code in which, you know, on a given day, 2 people went to a whiteboard, described, okay, we're going to get this to work this way, we'll share this common data structure, and then 2 weeks later, somebody else, they leave to go to Google because they got a better job, and then somebody else gets dropped in that code, and they say, well, no, I really don't understand this, I'm going to do it a different way, and these things kind of mount up and up and up. So there can be wars over the interpretation of specification where, okay, the code doesn't work, but it's not my fault, because any human being, if they read this spec, would do it this way, and the other person on the other side of the spec says, no, you clearly misread it. You can be spending an awful lot of time waiting on other coders to kind of calm down their code till you can finally, you know, rebuild it with your code. You can wondering why it was, you know, you left the office, you ran a build, compiled fine, regression seemed to be going fine, and then you didn't even make it through traffic on 101 before you get a cell phone call that the code's already broken and you didn't touch anything. So you have a sneaking suspicion somebody else later checked in some code just in those few minutes, and that broke your code. And then when you go back and try and verify, you do your unit tests and they're doing okay, but you know, then you do a little more build with the other code and it breaks, and it's hard to exactly identify, you know, which one of these innumerable data structures that I touched that somebody else touches broke. And obviously, if you can't even get this basic serial code to work, then it's hard to parallelize this code without identifying the key computations and kind of building a little sandbox that allows you to optimize your code. So modularity helps with all this stuff, and this notion of modularity goes all the way back to this Key Key article back in 1972, Composing Systems into Modules. But modularity is not enough, as we've discovered in parallel computing. And the reason is I think, encapsulated in the following. So here's a little quiz for the audience here. Is software more like a building or a factory? How many people think it's more like a building? And that is the software artifact. Once it's built, once the software is created, is it more like a building or more like a factory? How many people think it's more like a building? How many people think it's more like a factory? Okay, it's about 60-40. Okay, so you, sir, I thought I saw a hand over here. Why is it more like a building?
Because it still has its architecture when it's finished.
Mm-hmm. Okay, so the notion is that this, and this is, I have stood up in front of audiences in our own course, Software Engineering CS169, and used this analogy to death. Software is like a building, And again, modularity is important in buildings. Modularity is important in software architecture. Who wants to say why it's more like a factory? Oh, come on. Yes, sir.
You have you have different departments do with different things, and you combine everything together.
Yeah, so you're in some sense combining things together. And again, we're talking about the artifact of software, as it runs, right? But the thing that's so obvious about this is, buildings kind of sit there and just provide shelter, whereas factories take input, change it, modify it, and produce output. And in that regard, I've come to believe that they're much more like software. So really, the whole remainder of this talk is really about using this analogy. How can we think about this analogy as software as a factory, as opposed to software as a building, to help us build software? Now, note that every factory is a building. So this 35 years or so, no, I guess it's going on 40 years since Parnas' paper, of thinking of software as a building and the importance of modularity, all that works when we try to build or create a factory, right? All that principles of modularity help. But as we'll see, there's a little more to it than simply building a building. And the essence of this, and I think this has really been one of PARLAB's contributions to this whole dialogue, is the simple notion that what computations we do is as important as how we do them. Now, when I teach software engineering, I more or less delegate, or in the past when I've taught software engineering and use this building analogy, I've more or less delegated all discussion of computation to the other courses. Oh, linear algebra, okay, there's a course in that. Okay. Oh, no, graph algorithms, well, there's a course in that. Oh, discrete math, okay, you've already taken that, and so forth. We don't talk about computation. But our premise, as we'll see in the PARLAB, is that the computation is just as important as the program structure. And so what we've done in the PARLAB is take this monolith of computation and break it down to a number of particular computational patterns. These are 13 name brand classes of computation. These are a number of application areas that we've looked over here. Red, say in embedded systems, means that there's a lot of graph algorithms in embedded systems. This orange thing here means that there's somewhat less. Green means a lot less, and blue means bluer, bluish, means they hardly appear at all. Right? So we've identified kind of what we think of these as the atoms of computation, and we've looked at them across areas and seen that areas are very diverse in the use of the underlying computations. So what I want to do now is talk about, given the simple high-level observation, how do we use this to actually architect parallel software? So the first thing we do is we look at the software structure. And this looks a lot like traditional modular object-oriented programming. We have a set of structural patterns, and these go back to Garland and Shaw, pipe and filter, agent and repository, event-based invocation, layered systems, and so forth. And then for purposes of parallelism, we find we've added some others, such as the puppeteer pattern, the iterator, or bulk synchronous process, and MapReduce. And these describe how software is structured together. They do not describe what it, in fact, actually does. And going back to our factory analogy, this is the analogy of the layout of the factory plant. These structural patterns describe how do we actually want to lay out the factory. Then there's the key computations. And so when we have an application, we break it down into the same set of key computations. And what are the principal computations as we go through these modules, as we modularly structure our software? What are the key computations inside of each module? And this is analogous to the machinery in the factory. So the structure describes how it's laid out, and the identification of computations tells what the key machinery is. And again, if you like the factory analogy, I think it's interesting to me to think, well, gosh, why did we think for so long that we could get, no one would ever think of building a factory without paying a lot of attention to machinery, right? There's obviously an interaction between the machinery of the factory and how you structure it. And yet we've thought an awful lot about how to structure software without thinking very much about how we structure the computation. And so this machinery and the layout work together to, in the software, architect the whole application. So this is a real life application that I'll be telling you about a little bit later. And this is its high level structure. And then deep down inside we have particular computations like dynamic programming and graphical models. Okay, so I'm going to start then with that's kind of refining the basic approach we're going to take, and now I'm going to just show you a little bit of detail. I think I showed you 9 or so structural patterns, and I'm going to just show 3 of you, out of which we'll do some simple examples. So first, how do we define a structural pattern? It's pretty simple. This goes way back in the history of object-oriented programming. A structural pattern is simply built up of components, which is where the computation happens. Component is just where you put the computation. Connectors are where the communication happens between computations. A configuration is a graph of components, which are these where the computation happens, and connectors as edges. So this is a graph. The vertices are the components, the edges are the connectors. And then if we want a particular structural pattern, like pipe and filter, that can kind of be seen as a family of related graphs. So far, so good? Okay, so here's our inventory of structural patterns. There are 9 here, and people may have particular favorites that are not on this list, or they may have a variant or so forth. But basically my position is, I'm not sure in the year 2020 that the list will exactly be these 9, but I'm pretty sure that something like these 9 will be there, and maybe there'll be 1 or 2 others. But I don't think there'll be 14 others, right? I think this is a list we've been building over the last 3 years here at PARLAB, and it seems to have held up pretty well. And I'm here to basically tell you, you say, well, that's all fine for 25,000 lines of code, but I've got 1 million lines of code. Well, from my industrial experience, I saw we were able to build 25 million lines of code using basically a subset, the sequential subset of these architectural styles or structural patterns. So I do believe that these are the basic ways that you structure software. So I'm going to focus on just 3 of these, the pipe and filter, and then 2 of the parallel ones, Iterator, or bulk synchronous process, and MapReduce. So pipe and filter is pretty simple. The filters embody where the computation happens. And these filters, the key thing about them is they're pretty simple. They see input show up on their doorstep. They produce output, and that's it. They don't go off and then they appeal to some global state. Everything they do has to be based on the local state that they have. They have no global state. They have no shared state with other filters. So what are some of the examples from software that you know that have this basic structure? Come on. Shell language is certainly follows a pipe and filter structure, the pipes in the shell. What else? What's some software that you probably use every day if you're out there building software that follows this basic structure? Compiler. Give that man a cigar if you're a smoker. Okay. So yeah, that's my favorite. So you take a program, you scan it, you build the internal representation, you optimize it, generate codes, object code. At the high level, this is a pretty realistic view of how a compiler works. This is a logic optimizer, a world that I know well. This is pretty much how it works. Here's an image retrieval system. As a matter of fact, I'd go as far to say is that almost every significant piece of software, if it's over 5,000 lines of code, at the very top level, it looks kind of like pipe and filter, because when we describe our code, this is just what we do. We go to the whiteboard, and we kind of go, well, then there's this module, and this module, and this module, and then they connect back in this way. So that's pipe and filter. Okay, here's the iterator. So the iterator structural pattern basically consists of, we have an initialization condition. We do a bunch of stuff asynchronously. When the exit condition is met, then we iterate. Sorry, when the exit condition is not met, then we iterate, and then finally, at some point, the exit condition is met, and we go on. And at the point at which we check the exit condition, there's a little point of final synchronization, but before then, all these functions are performed asynchronously. So what's a good example of this one? What does this look like to you? Where are scientific computing folks, or anyone else? Yes, sir? Optimization algorithms. Yeah. We're trying to meet some optimization goal. We do a bunch of stuff until that is met. When it's met, then we're done. Good. Thank you. And so this is an example that we actually use in support vector machine training for machine learning. And this is essentially saying, have all points on this particular iteration met a particular error rate or within a particular range of optimality. That's a way of thinking about that. And then finally, MapReduce. Now, you can't be familiar with the web and Google these days without hearing the name MapReduce. But to us, we kind of go past Google. I mean, Google is certainly an instance of MapReduce, but we go back to the very early days of Lisp, where basically a map simply means a map stage where data is mapped onto these set of independent computations, and these independent computations are on independent data sets. And then the reduce stage are where the results of the map stage are summarized, i.e. reduced. It's that simple. This is what it means iconically. And so what are some examples of MapReduce? And again, we know the web applications, but how about those of you who are doing parallel programming, or those of you who want to think a little bit outside the web, what are some examples of where you might apply a MapReduce? Yeah.
Using ISR data from sensors?
From?
Sensors.
Sensors. Fusing data. Yeah, so you're mapping the computation of sensors on the sensors, and then you're fusing it back together. They're all independent. That sounds pretty good. Another example? All right, we'll go with that one. Thank you. So here's a couple examples. So what we find in the same support vector machine learning, when we're doing that evaluation, I just showed you that error condition or that optimization condition where we met. We compute basically the distance between any point in this vector space to a particular frontier that we've built. All those computations are independent, and then we map that computation out, and then we reduce it back together to see who's the farthest outlier from this frontier that we built. Or in speech recognition, we map this hidden Markov model computation, evaluate each word match, and then we reduce to find the most likely word sequences. Okay, so those were a brief set of structural patterns, and I only showed you 3 of 9, but given sufficient time, I could have certainly gone through all 9 of those in about the same level of detail. And now let's briefly touch on the computational patterns. I see I'm going to have to speed up just a little bit. So again, this is our inventory of key computations, and similar to structural patterns. I don't know that in 2020 that we'll have exactly this set of 13. I don't think it's going to be more than, say, 17, and I don't think you'll see any of these disappear. They might get folded into other more comprehensive computations. So what I'm saying is we're 3 years into this process. This is holding up pretty well. I go to diverse sets of computational people. I would do this presentation. I play, okay, now stump me, tell me a type of computation that you're doing that you think doesn't fall into this. And the worst that ever happens, what most happens is they talk for a while and go, well, no, that's Monte Carlo. I know you don't call it Monte Carlo, but it really isn't like this or something like that. Every so often, it's 45 minutes at the whiteboard, at which we kind of go, well, yeah, okay, I don't want to call it graphical models, but I guess you would call it graphical model, Kurt, so I can live with that. But if any one of you want to stop by and play that game sometime, I'm happy to do it. Because we're not, this whole research effort is out of pragmatism, not zealotry. We're not trying to sell the world on something that, we're pragmatically trying to figure out how to build parallel programs. So of these are 4 that I'm going to go through briefly today. So linear algebra, I'm not going to be able to do a tutorial on any of these computational patterns in like 2 slides per. But this is just to jog your mind in case it's been a while since you've been in a linear algebra class. You have a vector space. Here's a linear map. Matrices are those n by n arrays of things. This is what your linear equations look like. And here's your eigenvectors and eigenvalues. Okay, it's basically just that kind of stuff. And the key thing is, and this is a key point about the computational patterns, the point of the computational patterns is not just to go, okay, well, you had a tough job before, and now we're telling you it's linear algebra, and now you still have a tough job. The point of identifying these computational patterns say, you had a tough job, but now that we've identified that this is linear algebra, life just got a lot easier, because there's lots of other people who built stuff to help you with this, right? Okay, so this basic linear algebra subroutines are basically vector-vector, vector matrix, and matrix-matrix. There's a large body of libraries as well as intellectual literature, codified books and software to help you if you're doing these kind of computations. And here's kind of summarized in this this book by our previous speaker, Jim, and his applied numerical linear algebra. And there's a bunch of libraries out there to help you as well. So then there's the spectral methods pattern, which we're going to use later in MRI Reconstruction. So spectral methods, again, if you haven't had them in like probably 2 or 3 weeks of a class, then you're not going to get in this moment. But the simple way, I think, to think about them is just you have data represented in one particular representation, and spectral methods are a way of turning it into another representation. What's the point of doing that? Because oftentimes the new representation is much easier to work with than the old one was. Okay, so in particular, Fourier and wavelet representations are different spectral analyses that expose different properties of images, convenient for solving our problems, say in magnetic resonance imaging. And the good news here is that we can change these from the obvious order n squared matrix multiplications onto order n log n fast transforms. And furthermore, these order n log n fast transforms are easy to parallelize. So, and even better news is you don't really necessarily have to understand any of that, which is if you at least identify, well, I'm not exactly sure, but it looks a lot like to me that we want to go from this data representation to this data representation, and then life will be a lot easier. Chances are there's one of these 2 libraries or some other like CUDA FFT for GPUs can help you do that without you ever writing a line of code. Okay, the last computational pattern I'd like to show you is a very different one. The last 2 were very numerical. This one is very, in some sense, graphical in nature. And it's dynamic programming. And this covers a very broad class of problems for which the optimal solution for the problem can be built up from a set of optimal solutions to subproblems. And it builds on this principal optimality that, say, if we're looking at over a set of trees, that the optimal cover for a tree consists of the best match at the root of the tree plus the optimal cover for the subtrees. Okay, so, for example, if we're sitting here at the root, we have a particular cover, a way we're going to finish this computation at the root, then this is built up from the best covers for the subtrees, P and Z. So we identify the best for P here, and that includes that then in turn, in this recursive way, depends on the best covers for X and Y. And so here's a place where I personally applied dynamic programming, which is, this is a circuit. I think in the simple 2-input NAND gate inverter way, you can see that it's a circuit. And what we have down here are elements of a library that we could get from, say, LSI Logic or IBM or Intel. And we want to take this abstract circuit, just to describe in terms of NAND gates and inverters, and we want to optimally re-implement it in terms of these very efficient actual cells from this technology library. Okay, when I met this problem in 1987, it was seen as pretty hard, and as a matter of fact, In its core, it's taken off the shelf on general directed acyclic graphs. It's NP complete. But in fact, if we partition this into trees, then we can solve it in linear time. What I'm showing here, each of these describes a particular match, which corresponds to the element of a technology library. And then if we want to do an optimal match, then we simply build the matches going from leaves to root, just as I described, using the principle of optimality. This is one set of matches. This is another set of matches. This is the optimal cover using this and/or invert 2-1 here with the cost of 7, the NAND 2 here with the 3 being 10 versus the match of 13 over here. And this is also widely used in code generation for compilers. So it's kind of the same diagram, but different types of covers here. We're trying to cover an intermediate representation of a program with instructions, say for an Intel computer, and actually generate the code to then implement this little code abstract syntax tree. Okay, and here's another place where dynamic programming is used in speech recognition, where we're going along and we have a number of different hypotheses for how to recognize this speech. So this is recognize speech. Okay, these are a set of observations, and as we go forward, through this, at any given time, we have a set of hypotheses of what we actually recognize, build out of hypotheses for other optimal submatches, till when we get to the very end, we have some pause, then we use dynamic programming to find the optimal match. Okay, so what I want to do now in the time remaining is I briefly exposed you to a set of structural patterns. I briefly exposed you a set of computational patterns. And now what I'd like to do is show you, okay, how do we put these two together to actually architect real software? All I'm going to be able to show you are some kernels, but these are significant kernels that I'll be able to show you today. So the first is support vector machines. So in here, suppose we have, as probably many of us do, we got a bank here of pictures of the kids, a bank here of pictures of flowers, and what we want to be able to do is at least separate this into all the photos of the flowers and all the photos of the kids, right? Okay. So what we do is we train the classifier on a set of representative examples, and so we go through this loop. And what that does is it basically extracts a set of features and says, items with this kind of feature characteristic are on this side of the fence, objects with this kind of features are on that side of the fence, and it creates a particular frontier. And then we have a set of new images, for which, again, we do the feature extraction. We go through the classifier on this new set of images. We exercise the classifier, and we get out a result. And so in the feature extraction portion, we do reduce to a set of low-dimensional feature vectors. So we break down those images just into a set of features like RGB, histogram computations, and so forth. And we do that now. So this is a pipe and filter description of these 3 stages. That breaks down to a simple structured grid computation. This breaks down into a MapReduce, and at each cell of the MapReduce, then we have a dense linear algebra. This breaks down to, this build description breaks down to a MapReduce, followed by a structured grid, another one of our computational patterns. So if we kind of tilt this, this is showing this hierarchically. If we kind of tilt this on its side, what we see is here's the root of these, a simple pipe and filter structure, and then we go into the filters. Here we have another additional structural patterns, that there's more structure in this particular filter of the pipe and filter. There's a MapReduce here in each of these, and then underneath these are lower level computations. Okay, and this is not entirely cosmetic. This allows us to systematically architect this software in a meaningful way. Okay, then that was the feature vector extraction. Now we saw this before as an instance of the iterator. And so what we're doing here is we're iteratively building up a frontier where we find a set of, we do a computation seeing how far are each of these outlined for the frontier. If there's some particular element that's too far away from the frontier, in other words, basically we have a flower that's being classified as a child and it's too far away from the frontier, then we adjust the frontier here to include that flower, and then we iterate again until basically at least according to our feature vector set on the training, all the things on this side kind of look like flowers according to our feature vector set criteria, and all the things on this side kind of look like kids according to our feature set. So we have, on the outside, we have an iterator pattern. On the inside, we have pipe and filter, which is these two filters. If we pop open these filters, we have MapReduce. If you look inside these MapReduce, and say what the computation went in there, it's basically a single, like dot product type of computation. Okay, so that's in this portion. So we saw the feature extraction, the training classifier, and then finally looking at the exercising. And the exercising classifier is even simpler. Basically, we put the test data in. It's just a simple pipe and filter. We compute more dot products using dense linear algebra. We compute kernel values, sum and scale. We're doing a MapReduce, and then we're able to actually, at the end of that computation, every single element, every single photo in the vector space will either end up on one side of the fence or the other. It'll be classified as this is a flower or this is a picture of the kids. Okay, so with that, we were able to build a simple support vector machine mini framework that's achieved a 9 to 35x speed up for training. So I've kind of delved deeply into the software engineering aspect of this, kind of in some sense how to get this right, but the whole point of doing this parallel computation is to get it go fast, right? And in fact, we have been able to achieve speed ups in this. So we got a 9 to 35x speed up on training versus kind of the out-of-the-box software, and got a much bigger speed up, 81 to 138 for classification, and we published that a few years back at the International Conference on Machine Learning, and we've had about 1,100 downloads or more since the time of people using the software. Okay, I think I'll motor through this. I don't want to take any air break time, but I think Jim started left me about 5 minutes over. So I'll kind of go quickly through this. So here's another application that was very much a pull. We have researchers on campus here who are doing new approaches to MRI. Basically, the problem statement is pediatric MRI is really hard. Nobody wants to sit in an MRI for very long, but children simply can't sit still. And oftentimes they're told to hold their breath, and they just can't do it. So to really get the kind of MRI image that you need, oftentimes they're given anesthetics, which is hard on their system and can even be dangerous. And so what we'd like to do is make that's all going to go easier if the MRI time is just less. So we had some researchers on campus here who had MRI techniques which were able to go for the sample to go much faster. But then that left kind of a computational IOU that when you actually wanted to reconstruct the image, that could take an overnight computer run. Right? So this is clearly a case where parallel computation could help. And you might go, well, what's the real problem with an overnight MRI run? I mean, you just get the news the next day rather than in real time. Well, oftentimes the radiologist, wants to really know in real time, okay, do I need to take another image? Is this really what I need? Do I have the information I need to make the decision? And they don't want to keep calling people back. Okay, we need to reschedule you. Oh, no, it's going to be a couple more weeks. Sometimes the situation is much more critical than this. So basically, it was absolutely required that the reconstruction time of the image be about the sample time of the image. And so that needed to be minutes and not hours. So this is research we did with a number of MRI researchers in this field, and it basically boils down to this optimization problem here, minimizing this relative to some constraints, which in this architectural description that I've been talking about, it has this kind of outer loop of pipe and filter with a set of Fourier transforms as the computation here, linear algebra here, more Fourier transforms, more linear algebra, and so forth. And then if we pop open any one of these core computations in a kind of fork join or MapReduce type thing, we have another layer of hierarchy here with iter refinement over spectral methods. So the details are not as important here as the fact that in a systematic way we were able to architect this application and describe it. And again, we were able to get quite, game-changing speedups. We were able to get a 100x faster reconstruction, which brought this technique from completely unusable in clinical practice to entirely usable. And in fact, this software is currently in use every day here at the in use every day at Lucille Packard's Children's Hospital. And I've, enjoyed meeting the radiologist who actually sits there and, gathers this data. Let's see, and so the old reconstruction time was an hour, which made it, for example, for this particular one, which made it a total non-starter, but with parallel we were able to reduce that to a minute. Okay. Then finally, speech recognition. So in speech recognition, you have voice as input, just as I'm speaking now. You do some signal processing on that in speech vectors. Let's break that down to vectors in a vector space, so speech features. And this is all natively parallel. This is just like with the images, that's pretty straightforward. Now the recognition is a lot harder. That's what we focused on. And there's a number of popular serial recognition systems out there. And our question is, could we speed this up? So this is the architecture that we came up with. So again, I'm not going to focus on this feature extractor. That's quite easy to parallelize. But this is the software architecture that we built. Here are the overall guiding computations. There's a graphical model computation around dynamic programming. The dynamic programming will be clear in a moment. If we see how that dynamic programming proceeds, it's basically an iteration over a pipe and filter. This has 3 filters. Inside of each filter, there's a MapReduce. And inside of the MapReduce, I'll show you the computations in just a moment. But the core computations which are performed briefly here are, we're on a frontier of states, which are essentially exploring the hypothesis as we observe more and more speech. So just think of the word speech, as I'm saying here. It's broke down into little phonetic components. And so we have a set of observations of speech. And so to compute the likelihood that we're at this particular state of recognition, it depends on what's the likelihood that we're here, what's the likelihood of going from here to there, and what's the likelihood, given this observation, that we end up in that state. So those 3 get computed together to determine a set of next states. This is how we break this into an architecture. This is the iteration loop I showed you before, and these are the 3 filters which we perform. Sorry, and then each of these, as we saw before, is a MapReduce computation. And so when we go through and say we get a pause, it's time to end the computation, or let me actually start from this side. As we're marching through at any given state, we have a set of hypotheses states that we might be in, indicating what's the likelihood that we've recognized this fragment of speech. And then when we get to the very end, we go, okay, this is the winner, this is the most likely, and we use this dynamic programming then to choose that and spit out this fragment of speech. Okay, again, I'm emphasizing today the architecture, because that we feel is our value added, but I think it would be not so interesting to say, oh, we did this architecture, and of course, the software either never actually worked, or it worked, but it wasn't that interesting, but it was interesting of academic. No, the point is, when we go to these conferences, like, or when we publish in IEEE Signal Processing Magazine, or you see we often publish in the Interspeech Conference, we don't talk a lot about how we got these results. What we focus on is we got 11x speed up over the sequential version, which, if you compare that to our 100x speed ups, it's not as impressive. But to be honest, when we tell people, well, we got 100x speed up on this image processing, people go, well, that is interesting. That's a published result, but I'm not shocked. I'm not surprised. We see all this. When we go to these conferences, say, on this highly, graph algorithm and finite state machine-oriented computation, when they say we got 11x speed up, people are pretty impressed. That's been a very survivable result, and I think it's influenced the field a bit. And it influenced this researcher. This is a PhD from the Technical University of Berlin who saw our results. She came up, she had a Java program for doing speech recognition, which coupled actual speech recognition with visual data. And so the application there might be that if any case where you're speaking, but there's also the ability to have a camera right there to do some image recognition on the movement of your mouth, then she wanted to couple the audio of the speech recognition together with some video data as well. And she knew she could get, in fact, better final results on speech recognition if she did that. However, with her Java program and so forth, she saw no hope of it being applied. It was just way too slow. So she came here, and first thing we did is we recoded her speech application in C++, and then over even this moderately optimized C++ version, we were able to get a 20x speed up and publish a paper on that. Okay, so in summary, I just want to briefly say here that this basic approach that we have taken has allowed us to even though we're not deep experts in any of these areas of speech recognition or computer vision or computational finance or MRI or machine learning and so forth, we've been able to use these techniques and apply to a wide variety of areas and produce publishable results. And I think that focusing on the computational patterns, what I just find over and over is that even if I'm not an expert in an area, by breaking a computation such as MRI Reconstruction, such as speech recognition, such as computation of option pricing in finance, by breaking it down to a computational patterns, I go from an application area that's very unfamiliar into a set of computational patterns which are very familiar, and that's allowed us to do that work. Alan Kay says that perspective review can raise your IQ 100 points, and I don't know that I'd say that this is raising our IQ 100 points, but I would say that this perspective that's given us by breaking things into their computational patterns has raised our IQ point about 20 IQ points, which is enough for us to produce these results. And then plugging that back into the pattern language for actually architecting the code has allowed us to write good parallel code, which has been downloaded and used by a number of different users. Okay, and with that, I'm ready to take some questions. Yes, sir. And I think if you want to hold for the microphone. Michael, somebody want to bring the microphone down? It's coming your way.
Thank you. If I see a complex system like one of these that you showed, let's say for instance speech recognition or so, I see all these blocks, patterns that have been ordered. Then I wonder, was it like that? How did they arrive at it? When they were designing it, usually what I do in a almost small system is say, okay, first you go and look, where is my work efficient? So you start with one pattern and you say, I got to do that one.
Right.
And usually it's enough. But then I don't get 100% maybe. Sometimes I need to do look a bit further, but that's on the result of.
When you say you don't get 100%, you mean you don't necessarily get the performance that you want, or?
Pardon?
When you say you don't get 100%, I'm not sure 100% of what? 100% coverage of your system, or 100% of performance?
100% performance, let's say. There's a limit to the time I want to spend. There's a limit to cost of the design cost. So if I start by drawing up a whole system of patterns that I think are going to work, afterwards I'm going to find that 90% of them were not really needed. So I can understand that you arrive at a very complex interconnection after a lot of work by a lot of different people, etc.
Okay.
But I wonder, can you really do that from the start, get to the correct...
So let me, I think you've got two really good questions, and let me summarize them briefly here. So the first is, does it really work like that? That is this methodology with all the boxes and so forth. And I think it's a great question, which is, I think every programmer's experience is that it's kind of a middle out phenomena, and there's something about hierarchical diagrams that make it look very top down. So the middle out is as you described, either driven by computational bottleneck or by what you think will be the critical path of the system, or what's the part that you don't understand. You kind of delve into that, and then you take a step back, and you kind of go, okay, well, now how do the other pieces fit together? And then you go down again, maybe do a prototype, and so forth. That is the process. But these beautiful top-down hierarchical descriptions are a little bit where you land, not where you started. But the fact that you know that that's where you're headed does inform your thinking of how you do the partitioning, rather than just this kind of jumping into code and jumping out. And moreover, Michael, who's sitting right behind you, and David Sheffield, one of them just had on the speech code, the nice thing is once that code is written, we all know code spends much more time in maintenance than it does in creation, right? So once that code is created with that structure, they and another student's code, and I don't have a lot of experience of people in industry coming in and saying, oh, I really like this code that I was working with, but much less with student code, but using another student's code, they said they were able to get in and start re-optimizing it for a whole other platform in a day, right? So even though no one I know ever just kind of goes into a dark room and masterminds some sort of architectural structure and then just implements it top down, the fact that your thinking is informed in that way, and moreover, at the end, you are able to do a document that says this is exactly how the code is structured. It's very helpful for the people downstream. Now, you also mentioned, that's presuming you're doing kind of a white sheet of paper, we're going to start all over. I think there's also a very good question there about, okay, well, that sounds really good, Kurt, but we have 1 million lines, 2 million lines, 25 million lines of legacy code. We're not exactly about ready to just scrap it all, and start thinking great thoughts about how we restructure it. And there, I think it's a tougher question, and I wouldn't want to generalize, but in the pieces of code that with people in the industries I'm familiar with that I've gone in and taken a look at, what my advice was, I didn't roll up my sleeves and reorganize a couple million lines of code. My advice was that if you oftentimes re-architecting code not only can lead to better speed-ups, but it can actually, believe it or not, lead to less code modification. So let's do an A-B comparison. What's the standard thing? Is you go in, our code's not running fast enough, our competitors got something fast in the market, we think they're using multi-threading, gosh, what do we do? Okay, what's most people do, jump in, let's put some threads in, see if we can't catch up. As you do that, this threading code tends to kind of proliferate because the hotspot keeps moving around. Pretty soon you're modifying an awful lot of code to rethread. If in approach B, you re-architect, often you say, okay, here are the critical portions that really need to run fast. We need to re-architect those. And oftentimes it's like a MapReduce calculation or something. And the map function could be like 100,000 lines of code, right? You don't have to change the map. You're going to get the speed out of parallelizing that single computation many times across many cores, rather than trying to rethread code that 100,000 lines. So I know it's easy for me to stand up here and walk off and go back to my office and say, well, re-architect, don't just recode. But I do deeply believe that no matter how many lines of code you have, at least try to think of how you might re-architect it. And I think, particularly as we get to 8, 16, 32 processors, you're going to find you're doing less recoding overall if you take some time to re-architect. Thank you. Other questions? Well, those are two really good questions. Yes?
During the beginning of the presentation, you had mentioned about 2 designs of software design in which you talked about this. The second one, definition of invariance, which you didn't go into. Can you just elaborate a little bit into that?
If I stand up here honestly and talk about, okay, I'm not just trying to give a lecture on patterns or something. I'm really talking about how do you build software. I've talked a lot about modularity, software structure. I've talked a lot about the importance of computations. I would really talk about the importance of invariance because I have, in industrial context, seen two large software products, multi-million lines of code. One has we worked, both of them had a good architecture. Both of them have very strong modularity and so forth. One knew what their invariants were in every significant module. The other one had no idea what their invariants were. And the absolute invariance, good code structure is not enough. There's some modules that are so critical. If you just don't get them right, and you don't really know what you're trying to achieve in terms of correctness, then you can still go into oscillation. So that's my brief speech on that. Yeah. Thanks for the question. More? This gentleman has. Well, how about one more? Just one question. First, can somebody, while you're waiting for my question, you're supposed to have like a break now till when?
It's actually in 5 minutes, and it's going to be a 30-minute break, so you still got 5 minutes for
Okay,
questions.
great. Sorry. Okay, thanks. Yep.
I have requoted your quote by Alan Kay about these 20 IQ points. I found out that it's true, but I'd like to know who Alan Kay is, and so next time I can quote him correctly.
Yeah, so Alan Kay, you can Google Alan Kay, and you can Google perspective or point of view. And he is a researcher at Xerox PARC, I believe, and he was one of the early people on the alto. If anyone knows better, then they can correct me. And he's one of those kind of futurologists that gets trotted out every decade, because every decade people rediscover what he did back in the 70s or so, and then he says, no, it all goes back to Ivan Sutherland and the sketch program at MIT and stuff like that. But I mean, but this quote is, I think, brilliant. And I think, particularly as we see ourselves going to a flat world, there's a sense that everybody's going to have the same perspective, everybody's going to have the same advantages. And I think there's something true about that, which means that if you're in a flat world, if your hill's just a little bit bigger than anybody else's, then you really see a lot more than anybody else. So I actually think his quote, the perspective or view is worth 100 IQ points, is becoming even more true in a flat world than it was before.
Thank you.
Okay, well, we're exactly on time. Last question? Okay.